Can you hear me? Okay. Thank you for the introduction. So this is me while I do cliff jump, and I am a security researcher at Shielder with a wonderful team. And I am also part of a NGO called osservatorionessuno.org. And you can find me on Twitter at the handle TheZero. And this is the agenda for today. We will start with an introduction on the blockchain and on smart contracts. Then the second part will be the Web3 perspective from a Web2 developer going into Web3. Then we will switch our point of view to security researchers from Web2 going into Web3. Then when we have some basic concept, we will do some root cause analysis of some of the best vulnerabilities in the Web3 world. And at the end, we will do some closing remarks about the concept that we learned. So some disclaimers. This will not be a buzzword talk. I will not try to sell you Shielder coin in an ICO. And instead, the objectives of the talk are to understand the concept behind Web3 and the smart contracts, and to learn new offensive and defensive concepts, both for security researchers and developers. And please don't use the code that you will see in the slide in production, because it's not safe, it's not reviewed, and you shouldn't do it. So let's start our journey with a brief introduction in this new world. And nowadays, everybody knows what the blockchain is. And raise your hand if you have heard the word blockchain or smart contract or something like that. Okay, I see quite a few hands. And basically, the blockchain is a public distributed immutable database. And what does this mean? It is database, so it is a place where we can store different type of data, and it depends on the type of blockchain. And it is immutable because once some data is added to the blockchain, it cannot be altered or modified, and it's there essentially forever. And it is public and distributed because every node and every party peer of the network gets a copy of the data. And this data is public, so everyone that gets a copy can look into it and have access to this data. And the blockchain started to evolve, and at some point, Ethereum came up with the concept of smart contract. And smart contracts are like digital contract between parties without a third party that rules over the contract. So we don't have a public notary like we have in Italy. And a smart contract is a collection of code, so the function of the contract, and the data, so the state of the contract, that reside at a specific address on the blockchain. And it is the code that enforces the rules of the contract programmatically. And like everything else on the blockchain, a smart contract can hold and send money, so it can transfer money. It cannot be deleted, and it cannot be altered. Once the contract is deployed, that's it. And the interaction of a contract and to a contract are irreversible. This is an example of a small contract, and it is developed in the Solidity programming language. And at the first line, we have the declaration of the Solidity version and the compiler version that we will be using to compile this code. At line 3, we have the definition of the contract. In this case, the contract is called greeter. At line 4, we have a variable inside the contract called greet of type string. Then we have a constructor, and this constructor is only executed once per contract. So this contract constructor will be executed once when the contract is deployed. And then we have at line 10 a function that is called greetings, and this function accepts a string it's public and returns a string. And how can we go from the source code that we just seen to the blockchain? And basically, we start the flow with the source code. We fed it to the Sol-C compiler, the Solidity compiler, and the compiler gives us output 3 main parts. So the bytecode on the left of the contract that is executed, and then we have the runtime at the center. That is a special type of bytecode that is executed only once, and it's used to deploy the contract on the blockchain. And in the runtime, we actually have the constructor. And then we have the JSON ABI, that is an abstract binary interface inside the JSON structure that is used for contract-to-contract interaction. And you can think of that like a Swagger or a VSDL file or a symbolic file for if you are like into reversing and binary. And I talked about bytecode because the bytecode of the smart contract is executed inside a virtual machine, specifically for the Ethereum cryptocurrency inside the EVM. And this virtual machine allows us to build a distributed computing infrastructure, and the state of the execution is stored on the Ethereum blockchain. So we are executing stuff in a distributed way, and the state is on the blockchain. And this virtual machine has a risk instruction set, and we will talk about it later. So once a participant of the network wants to do and interact with a smart contract, basically they broadcast an execution request to the network, and the execution causes a state change that is committed inside a transaction and propagated to all the peers of the network. And this results in distributed execution. Let's see in depth how this works. This is Bob, and Bob wants to interact with a smart contract, so broadcast his execution request, let's say, and to the network, and then every node of the network gets the execution request, execute it, verify that the execution is correct, and then update the local blockchain after a miner validate the transaction. So how can we prevent the flooding of the network with execution requests? Because every peer can request executions. And the Ethereum developers came up with the concept of gas, that is to waive the computational effort and the state change that an execution will make, and so make the user pay for it accordingly. So this concept make the EVM a quasi-Turing complete machine, and we don't have halting problem here, because once the gas is done, you need to send a certain amount of gas, and when the gas is done, the execution is stopped. And smart contracts need to be deterministic because everybody in the network needs to have the same result, and this is important. So let's start our journey looking at Web3 with a Web2 developer point of view. And for the developers in the audience, let's assume that your boss works in your office and asks to you, hey, we need to make a Web3 version of our product. And so the first concept that you will encounter is that, as I said, the public execution and the public state of the execution is distributed, and everybody can see the smart contract bytecode and the smart contract state. So everybody can see the values of the variables that you are using during the execution of your contract. So smart contract should be treated as client code, like the JavaScript that runs on your browser or the mobile application on your phone. And since you wouldn't check an admin password inside the browser, you wouldn't do it inside smart contract. And if you're doing it, consider upgrading and changing and fixing this bug. But then you come up with the second big concept, that is that you cannot really update your implementation once it's live on the blockchain. And your contract will be available forever until you call the self-destruct instruction inside it. And the self-destruct instruction is a special instruction in the virtual machine that tells everybody that this contract cannot be used and you cannot interact with it anymore. But the state of the contract and its bytecode will still be in the blockchain because it was deployed in a previous transaction. So how can you prevent pushing vulnerable code on the blockchain forever? By testing before deploy. Here is really important, and you should avoid fast prototyping, so going live as soon as possible. And there are a lot of development tools that can help developers with this, and you can also use testnet blockchain or offline blockchain for it. And a mechanism like updates can be done with proxy contract, and this is Bob again that wants to interact with your contract. And instead of making Bob interact with the smart contract directly, we instead build a proxy contract in the middle and then the real implementation contract behind it. So you, as the owner and the developer of the contracts, at some point can change the linking of the proxy contract to link to a different contract. And all the proxy contract is doing is taking the input from the users and forwarding it to a smart contract. And you ask, why these don't violate the immutability property that we saw? And this is the code that is used to implement it. We have a proxy contract, and inside the constructor, we set the contract set its owner as the user that deployed it, and set the default implementation with an address of a different contract. So inside the implementation variable, you have the address of the contract that will be linked. And when you want to upgrade the contract, you can call the upgrade function, passing an address as the imp variable, and it will change the implementation address. And from now on, all the input from the user will be forwarded to a different contract. And this function can be called only by the proxy owner, since we have a modifier that checks for it without require. And so this way, the proxy contract bytecode is still immutable because all it is doing is forwarding stuff input to a different contract. And you are lucky because, as we have seen, smart contracts are usually small, so you can read the whole code and spot easy bugs. And so also the efficiency is greater because they are small. And but it's JavaScript, so you are reading JavaScript, and in reality, it's worse than JavaScript. And this is a quote from Matteo Di Piero's master thesis that says that Solidity type system is not safe, and contract interfaces are only consulted and looked up at runtime, not at compile time. So if there is a problem in contract interfaces, the EVM raises an exception and the user wastes their gas, because for executing it, you need to pay gas. And another funny thing of the Solidity compiler is that at some point decided to calculate 1 with exponentiation, and actually a lot of smart contracts were doing 2056 to the power of 0 instead of putting 1 as a constant, and this cost people money. And this is a big what, and remind me about Gary Bernard talk that explains other funny stuff in programming languages and compilers. And yeah, Solidity is bad, but it's still in an early stage, and unlike CPUs, the EVM and the compiler can evolve at speed, and most of the time, we can kill vulnerability classes with breaking changes, either in the VM or in the compiler. For example, this is a vulnerable smart contract with a buy function. And inside the buy function, we can see that it takes a variable called num tokens. And this variable num tokens is multiplied for the price per token constant. And then we have a require that checks if this condition holds true and is checking if how many coin we are sending is equal to the number of token we are asking times the price per token. But if we ask for a big enough number of token, what happens is that the multiplication will overflow and wrap around, so we can send few coin and get a lot of token. And this is funny because the Ethereum developers managed to implement like overflow in a language that was released like in 2016 or so. And we have another bug here, namely Sol 2018-4 with a small smart contract. And in line 3, we have a declaration of a exp variable of type uint8, and it can store up to 255. And we assign to it 2 to the power of 8, that is 256. So we will wrap around the exp variable, and so the value inside it will become 0. Then in the following line, basically, we do 0 to the power of exp. So in theory, we should be doing 0 to the power of 0. And in version 0.4 or less of Solidity, this outputs 0. And that's what? It's wrong. And in Solidity 0.4.25, the output is 1. So it's coherent with math, but still not ideal, because we are still overflowing. And with Solidity 0.8.x, the execution is reverted because the compiler, actually the EVM, see that overflow happen, and so the entire execution is reverted. And how solc 0.8.x revert the execution on overflow? And basically, it adds new bytecode at compile time that guards against this kind of scenario, like stuck canary. And this version of Solidity is pretty new, and it came out like this year. And this adding this new bytecode that is added obviously is more gas expensive, because every bytecode and every extraction that is executed in the EVM use gas. And so developers started using the unchecked keyword in order to disable those checks and save gas. And you shouldn't be doing this. And yeah, it's important to minimize gas requirement, but we need to do it. You need to do it in a safe way. And we need to minimize the instructions that are executed and the storage that is used. And for example, here we have 2 contracts, and they have the same function beside the first one that implements an assert call that checks if the input array length is less than 256. And in both contract functions, we have a for cycle with a uint8 index and a condition that says if the index is less than array length. And here you can see the opcodes that implement the assert call and how much gas they take. And if we send to the 2 different contracts a small enough input, we can see that without the assert, we gain 26 units of gas. But what happens if we send a large enough array? In the first case, the assert will stop the execution and use a limited amount of gas. Instead, if we don't have the assert, the index was declared as uint8, and the input length here overflows, and so it will become an infinite loop, since the condition of the loop will never be true. And in this case, the user that is calling the smart contract lose money, but there are also cases where the owner of the contract lose money. For example, this is the case of Parity Wallet, and maybe you heard about it. And at some point, a random guy on the internet killed the contract. And how was this possible? Basically, Parity was working in a library way, so kind of a proxy. But the first contract that the user interacts with is a personal contract, and the owner is the user himself. And then we have a library contract that is used to implement all the logic so we can minimize the gas cost. And if we have multiple users, each user have a personal contract, and all the personal contract interact with the same library smart contract. And what happened is that the contract at the bottom was created and deployed on the blockchain at some point on July 2017. And the attacker noticed that nobody actually initialized the contract. And so in November 2017, he called the initialize function, setting himself as the owner of the contract. And at that point, he killed the smart contract, calling the self-destruct opcode. And here we can see the contract is not possible to interact with it. It's self-destructed at some point. And the balance here is only a couple of millicents of Ether, because all the money was in the personal wallet of the users, not in the library wallet. So I hope I haven't scared too much the developers in the audience, and we will now change our focus to security researchers. And maybe there is this trend among security researchers that Web3 exploitation is like binary exploitation is a trend, and everybody wants to go as low as possible. And I have to tell you that Web3 exploitation is as low as binary exploitation. And we will start with the EVM. And the EVM, as I said before, is a risk-averse architecture. And is risk because there are only 140 defined opcode and instructions with a hard limit of 255. And it is a stack machine. So values are put in the stack, and then we can execute operations on the value in the stack and get the result in the stack as well. And if you ever played with Dalvik or Lua, they are stack machine as well. And you can easily prototype the architecture, since it is really simple, and you can like emulate it with Python and with all your favorite programming language. And doing research for the EVM is like doing cutting edge binary like research, because we have symbolic execution and formal verification as the norm. And there are like a lot of tools that allow you to do this kind of stuff. For example, Manticore, Mithril, Shilling. And if you haven't, I've posted a blog post on shielder.it about using Shilling to reverse smart contracts. And so since we have all this kind of fancy stuff, finding low-hanging fruits is really easy. And symbolic execution can give you the exact input that you can send to a contract in order to exploit it, like autorop from Pontool, if you are a pawner. And the key here is automating all this stuff and scan new blocks in the blockchain, and so exploit vulnerable smart contract at scale. But the bad news is that also developers have these kind of tools, so they kill low-hanging fruits before going into production. And most of the live bugs are either logical or financial. And I have to teach you some new concepts about financial and economics, and it will be easy. The first concept is shorting, so selling an asset without really owning it, so lending it from someone else and buying it later when the price is lower. And the concept of stablecoin, that is a cryptocurrency whose value is fixed to the value of another currency, for example, the US dollar. And this kind of cryptocurrency, like they have a $1 value fixed, for example. And some month ago, an attacker tried to short Bitcoin and used the Terra stablecoin in order to do it. And basically, this was the plan: to first loan some Bitcoin, a big amount of Bitcoin, then buying a lot of Terra coin with the Bitcoin, and selling 35K of Terra for 34K of US dollar coin. And these two are $2 stablecoin, so they should have a value of $1. But if you sell different amount of them, obviously one of them needs to have a smaller value than the other. And so the value of Terra started to go down, and people went literally panic mode and started selling all their Terra coin, crashing the market. And this is what happened, and that's a really bad slope in economics. And so the Terra Foundation, the developers behind the Terra stablecoin, started selling big amount of Bitcoin in order to keep the price high and keep their reputation high. And at this point, the attacker simply sold everything and buy back Bitcoin at a much, much lower price. At this point, the attacker also closed the loan, the initial loan, making a big profit. But if you want to stay technical and not go into financial and economical vulnerabilities, we'll still have technical vulnerabilities not limited to smart contracts. You can find bugs in the compiler or the virtual machine. You can find bugs in other virtual machines, for example, the Optimism attack by Saurik, the guy behind Cydia for iPhone. And you can find cross-iteration, cross-chain interaction bugs, flash loan bugs, and you can even come up with new attack classes and attack scenario. And this field is really wild. And now we can, now that we have some basic knowledge, we can start some root cause analysis of Web3 vulnerabilities. And maybe you saw the workshop from yesterday by Riando, and here we will do some root cause analysis in depth. And the first big vulnerabilities that happen is the DAO hack. Maybe you heard about it. And the DAO is stand for decentralized autonomous organization, and basically is a distributed investment fund where there is no authority that select where the fund is going, but there is a voting system that decide which proposal gets the investment from the investor. And this is all done with the smart contracts. So there are smart contracts that raise funds from investor, and there are smart contracts where voters can vote proposal, and then when a proposal is founded, the profit inside the smart contract can go and will go to the investor that actually invested in it. And there is a concept in the DAO that is that if a minority of the investors object to a proposal of funding, and this proposal is going to be funded, then the smart contract literally splits the founding and allow the minority to retrieve the fund at a later time. And I written a small and easier version of this DAO contract, and it was like really big. And basically, there are three main parts. The first part inside the buy token function is implemented to send coins to the contract and store them inside a pot. Then there is the transfer token function that is used to fund a proposal, so to transfer money to other people. And then there is the withdraw function that is used to retrieve coin whenever like a split happens. And the vulnerability lies here inside the withdraw function, because the contract is transferring the coins before updating the balance of the user that requested the transfer. And if we zoom in, we can see that the function withdraw accepts a recipient, and recipient is of type address, so it can be a wallet from a user, but can also be a smart contract. And at line 16, we just check if who is asking for a withdraw have some money actually. And then at line 17, the call method is used on the recipient, and this call method will transfer money, but if the recipient is a smart contract, will also transfer the execution to the smart contract. And it will be transferred the execution to the recipient fallback function. And in this way, the fallback function inside the recipient can basically call again a new withdraw with his address as the recipient, and this will be a recursive function call. And the balance will never be updated, because we arrive at line 17 and then we call again withdraw at line 15. And if you lost me at explaining the code, there is a simple flowchart, and there is a malicious contract on the right and the DAO contract on the left. We start from an entry point of the malicious contract that call the withdraw function of the DAO, putting himself, his address, inside the recipient variable. Then from the withdraw, we execute the call method of the recipient, and the execution and the coin are sent back to the fallback function of the malicious contract. And at this point, the malicious contract call withdraw again, and the cycle repeats without ever updating the balance of the user in the DAO contract. And I know this is confusing, but if you ever heard about reentrancy vulnerability, this is what it's all about. And the attackers that exploited this vulnerability gained $55 million, and actually it didn't really gain this sum of money, because the network decided to perform an hard fork and exclude the hacker's transaction from happening. And this was only possible because the majority of the network decided to do so. Because as I said before, transactions are not reversible, but if enough peers of the network decide so, that it can happen. Another nice vulnerability that I will explain is the FOMO 3D hack. And FOMO 3D is a gambling game made of smart contracts where players can buy keys from a contract, and the money will go inside a pot. And a time counter will be initialized, counting back from 24 hours. And every time a user buys a new key, 30 seconds are added to the counter, and also the key price increase. And when the counter hits 0, the last player wins the majority of the pot, like a downward action, sort of. And we need to find a way to delay others' transaction, and this vulnerability is called block stuffing. And basically what the attackers can do is to submit a lot of transactions that will use all the gas, and there is a hard limit for gas inside a block. And if we reach that hard limit and we pay enough fee for the gas, miners will prioritize our transactions since they are more profitable, and so will delay others' user transaction. And this is evidence of the attack going from the bottom to the top. We can see a block that contained at the center 103 transactions and only taking 50% of the gas on the left. And from that block on, the number of transactions decreased as low as 3 transactions inside a single block with all the gas for the block limit used up. And when the attack finished, we have on the top a block with 166 transactions and all the gas. And basically, this attacker froze the blockchain for everybody else, and only they could do transaction, and only they could buy key from Authority, but also using transaction for the whole blockchain. And was it worth it? And the attackers spent more than 80K units of gas worth of money, and gas and Ether, so Ethereum are the same thing, but gained much, much more Ether. So this is the end of our journey. Let's see some closing remarks. For the developers in the audience, remember to avoid rapid prototyping. If your boss come up to you and is strict about deadlines, tell him that you have my approval, and do a careful design before actually deploying your solution inside the blockchain, and test before deploy. For the security people in the audience, my advice is to jump on the Web3 train. We are doing a lot of cool stuff. And it's an opportunity to learn new stuff and to apply your knowledge to a different field. And maybe you can find the next million bug and offer me or us a beer. And that's it. I hope that you have learned something new today. Yeah, if you have some question.
So the lunch is approaching, will be short.
Okay.
Just in your opinion, what will be the technique that someone will use to deploy some attacks after the proof of stake merge?
The proof of stake will not change so much because it's just the way that new blocks are created, and we will not have block stuffing vulnerability anymore, for example, because that's based on proof of work. But all the vulnerabilities inside smart contract and inside the EVM or compiler, they will still be there. So they will still apply after the merge.
Other questions?
Yeah, as we heard from the others, from the first two talks, lots about bug bounties. Is there something similar into Web3? How things are doing there?
Yeah, the field is moving. There are a lot of companies that accept bug bounties. So also the price for the bounties are higher than for other type of vulnerabilities, and the payout is well. Thank you.